I'm going to talk about some work which involves quantum information theory, the Definetti theorem, as well as black hole physics, and this is together with one of my PhD students, Jinsao Wang. So imagine a cosmic or a very big kind of scattering experiment where you do the following. And this is kind of depicted on the left. And for those who are familiar with Penrose diagrams, they also see that it's also depicted on the right. But if you look on the left, there are four stages of this experiment. So you start on the bottom with the first. You start with a shell of matter, if you like, and you throw in this shell in a radial way such that ideally all the matter would actually hit one single point at the center. So you shoot it towards this green point, which is basically the, let's say, the coordinate origin. And by the way, on the right-hand picture, you see a green line going up. That's also this coordinate origin. So the right-hand side you should interpret as a space-time diagram where space also goes up, but you only see the radial direction. So the shell looks like something, okay, at the beginning it doesn't look like it's going in, but you see later it's kind of moving towards radius 0. So I'm not going to explain the right-hand diagram, that's really more for the experts. Okay, but here you see the shell, the blue shell, and now, as you know, if matter is too dense, and this is going to happen at the finite radius, this shell will actually form a black hole. So at some point, and you can always find this radius depending on the mass of the shell, and this will happen, and what is depicted in red should be the horizon of this black hole. By the way, on the right-hand picture, the horizon is this diagonal line. A black hole horizon, these Penrose diagrams are always diagonal lines. By the way, for those who are not familiar with the diagrams and still want to get something out of the right-hand side, you should regard them as diagrams that just show the causal relation. Because what is special to these Penrose diagrams is that causal relations are such that some point is in the causal future of another one if it's in the future light cone with 45 degrees. So that's why everything else is rather distorted. But you see that if you enter this black hole, if you cross the red line, you will not have a causal future outside. You will hit this wiggly line, which is the singularity of the black hole. However, you may have heard that black holes radiate. This is Hawking radiation, and that's also depicted on the second panel. Then what happens as a black hole continues to radiate, it will shrink, its mass gets smaller. So this you see on the third panel, the black hole is already very small. And by the way, the third panel corresponds to the time slice on the right-hand side with the number 3. And then at some point, everything has evaporated away. So that's on the fourth panel, you just have radiation left, and you can try to capture this radiation with some sensors, which I assume that are very far away from the black hole. So they're so far away that when you start to capture radiation, the black hole in a way has already gone, if you like, in these time slices that I've drawn. Okay, so that's the experiment. Now we can ask a question. This is, as you look at it from far, really a scattering experiment. You shoot in matter and you get out radiation. So that's what happened. You could for the moment forget what happens at 2 and 3. You just start with something which you may assume is in a pure state. So that's what I've written on the bottom. S stands in the following always for the entropy, for the information theoretic entropy. And I assume that this matter, this shell, is prepared in such a way that you have 0 entropy about its degrees of freedom. So it's a pure state, as we would say in quantum information or quantum mechanics. And then at the end, you have this radiation. That's the end product of the scattering experiment. And this radiation also has a certain entropy. And now you can ask, what's the entropy of this end product? Now, if you believe in the unitarity of not only quantum theory, but quantum theory combined with gravity, then you should immediately say S of R should also be 0, because that would correspond to unitary evolution. That's true for any scattering experiment without gravity, and so if gravity is somehow similar, this should also be the case. So this is a long-standing question, is SR really 0 or not? And there have been several answers to that. And basically the deviation or the discrepancy between the different answers is known as the black hole information puzzle. So there's on the one hand a calculation, an explicit calculation by Hawking and also many others who reproduced it in many different ways, which actually looks at the microscopic degrees of freedom of the radiation. So it's really looking at the details. It checks whether the actual quanta of the radiation are correlated with each other. And the outcome of this calculation is that they are not. And this is shown on this diagram. So what you see on the horizontal axis is kind of the amount of thermal entropy that is radiated away. So thermal entropy here is defined in a rather kind of straightforward way as just the amount of energy that has been radiated divided by the temperature. So this is the way you usually define entropy in just phenomenological thermodynamics if you don't know the degrees of freedom, the microscopic degrees of freedom. So the right-hand side is basically how much is there, how much radiation. And then the vertical axis shows the entropy of the microscopic degrees of freedom of the radiation. So the information theoretic entropy. And Hawking found that this just grows until the black hole has completely evaporated. And we assume that the whole radiation is S0. That was the initial entropy of the black hole, if you like, or the size of the black hole. So on the right-hand side of this diagram, the black hole has gone, and everything is radiation. Now you see, if at the end, so what Hawking's calculation says is that at the very end of the process, the entropy is very large. So it's maximally away from zero. It's really a maximal violation of the unitarity principle of quantum mechanics. However, you can also do something different. You can just ask yourself, what happens if you just suppose everything is unitary and then do the calculation? And this is what Page did famously, and he found this curve which says at the beginning the entropy increases, and this is clear because the Hawking particles, the radiation particles, are entangled with something that is in the interior of the black hole. And if you just trace out the interior, if you only look at the radiation, then of course this is a mixed density operator and the entropy grows. But as soon as half of the black hole has evaporated, so if it's half is in the radiation and half inside, then the entropy starts to decrease because the entangled partners of the radiation also get out, and at the end everything is out of the black hole and you have a pure state of what remains. So that's what is often called the Page curve, and this Page curve has this transition at roughly the half radiation time. So it's not exactly half the time in normal time, but it's after half the radiation has escaped. And so the question is now, how can we reconcile these two things? And as you probably know, there has been a very long discussion in physics, a still ongoing discussion about the question which of these curves is right. They're maximally different at the end, but this is really a fundamental question. Is the world still unitary or not if you include gravity? Now, quite recently, I think 2 years ago, there has been a lot of progress in this question. So this was for a long time just essentially two statements that couldn't be compared really. And now people working in quantum gravity and doing calculations actually started to get an understanding of what's going on here. And the understanding is something that is really interesting. So what they did is they applied a technique to calculate the entropy, which is called the Replica Trick. So what is the Replica Trick? So instead of looking at the von Neumann entropy, you look at the so-called Renner entropy of order n, from which you can retrieve the von Neumann entropy if you like. I will not go into that, so let's just compute the entropy, the Renner entropy of order n. So Renner entropy of order n is defined like that. See that here? And the important observation is that the Renner entropy can actually be seen as an observable. So what does it mean to see it as an observable? You can measure it with an operator tau n, which acts on the state, but not on the state of one copy of the system, but on a state on n copies of a system. So if you want to calculate, or if you want to measure the entropy of a system, the Renner entropy of order n, you have to prepare n systems and apply a certain operator. It's actually a swap operator, but I'm not going into that. And then you get as the expectation value of the entropy out. So in that sense, it's a measurable quantity. Now, you see, I mean, I always use these pictures now that you've seen here on the right, just as a picture for the black hole. And the only thing you should know about this picture in the following, because I will show it several times, is that, so the picture starts here, this is the 0 time, and this is the matter that goes in. The matter disappears in the black hole, that's the interior of the black hole, and here reaches the singularity. But there is also radiation coming out. These are these not so visible red things. Actually, Hawking radiation is not very visible, it's very low temperature. And then you see, you have here the detectors in the future. So this R region is kind of, this is, causality still holds here for the diagram, but I hope this can be corrected. So the R region that I've drawn is kind of where the detector is in this space-time diagram. So there is kind of, in this space-time diagram, a region where you create the matter, the start of the scattering experiment, and there is a region where it ends, and this is where you have the detectors in this, this orange detectors. I will always show them in orange. So maybe that you should remember. Blue is always the initial thing, it's the matter, and the orange thing is the detector. And this little triangle that you have seen on the left is always the interior of the black hole. That's the only thing you need to know. Interior, initial state, final state of the radiation. Okay, now you see here this diagram, and what you see in this diagram, you can say if you have 2 copies of a black hole, that's now a black hole here, the interior of one black hole, the interior of another one. What you need to do is to apply the operator in the case where n is equal to 2 to 2 copies of the black hole, to the radiation of 2 copies. So if you want to measure the entropy of the radiation, you need 2 copies of this black hole radiation. Of course, you may also go to larger n. And the way people now calculate that, so we don't have a theory of quantum gravity, and you can ask, how do people now do calculations? So they go into a certain half or semi-classical picture where they assume that the radiation, and so is described by a quantum field theory, and the geometry of the black hole is assumed to be kind of still a classical geometry, but you, like in the Feynman path integral, you sum over all possible geometries that are there. And this is now the interesting part, because you see, this is the inside of the black hole, which I've now shaded, and the boundary conditions, so to speak. So every Feynman path integral has boundary condition, initial boundary conditions. This is the matter and final boundary conditions, if you like, the radiation. And these are the things you see, but you don't see the inside. And Feynman now tells you that you have to sum over all possible inside geometries. So that's what these people did. And the amazing finding in the last 2 years, which really led to all the progress, among them by these people, Almairi, Mahajan, Maldacena, Pennington, with a separate paper, and Zhao, in 2 years ago, they found that among all geometries, you also have to consider geometries that actually connect the 2 copies of the black holes. So just create the 2 black holes to basically calculate the entropy or measure the entropy. And now what the half integral formalism tells you is that there is a geometry which connects these 2 copies, and this connecting geometry is sometimes the dominating contribution. So you actually have to really look at this geometry. This is a calculation that, so one could say Hawking kind of forgot this contribution. He didn't consider like taking copies and connecting them by wormholes. Now, this really looks kind of, okay, I will not go into the physical interpretation of wormholes. I just tell you that if you now do that for larger n, what it tells you that if you now calculate the entropy, the Renyi entropy of order n for large n, you actually have to consider a geometry where all these n copies of the black holes are connected. So what the calculation really does, and this is kind of the remark here, you actually calculate something that is for n copies of the radiation. Now it gets even a bit more crazy. For those who haven't heard about that before, this maybe sounds completely crazy. You can also ask, so if you, okay, maybe I should say these calculations then reproduced the unitary curve. So with these calculations, you really give support to that behavior and not that one. So these additional wormholes pull the entropy down to 0 at the end. So that was basically a confirmation that the unitary picture is, or this at least gives support to the unitary picture. But people could go even further, because if the unitary picture is correct, you should be able to kind of, from the radiation, retrieve information about the initial thing that goes in. And they also looked at this in the path integral approach, and they also did it, you have to also think operationally. So to recover information, you need to apply a very complicated unitary that basically simulates a black hole. So you simulate a black hole, and what the calculations show is that this is basically the simulated black hole on a quantum computer. The Feynman path integral tells you that the real black hole will also be connected by a wormhole to the simulated black hole. And then from that, you find the result that indeed, from the radiation, you can get back the N. So as I said, if you haven't heard about this before, this sounds probably pretty strange. So let me tell you something much more, let's say, down to earth, which was the other part of the title, and at the end I will connect these two things. Okay, this is the quantum definetti theorem. The quantum definetti theorem, in the version, I'm presenting it here, which is not the original version. It's a version I've developed together with Omar Fazi in a paper where we actually had a different purpose than developing definetti theorems. We consider a channel, and you see, I mean, these labelings are not by coincidence called N and R. This will be the state of the initial matter shell that goes in, and R is the radiation. And you can say, okay, this whole experiment generating many radiating shells, or many shells that go in and collapse to a black hole, and retrieving the radiation is just an enormously big, completely positive map, according to quantum theory. But you don't need to think now of black hole physics. So just think of a very big map that takes capital N many inputs and produces capital N different outputs, and make the following important assumption. Assume the map is permutation invariant. So this is actually something that operationally can be realized by just randomly permuting the input, and then when you retrieve the output, you apply the reverse random permutation. Then the resulting map is actually permutation invariant. This will be important. So permutation invariant is something we can enforce operationally. Now what the definetti theorem tells you is that if you now look at only a part of that channel, so you only look at input or outputs R1 to Rn, then the channel has a very nice form. Namely, it's basically just the product, so this means the n-fold product of a channel that I call T of one single M to a single R. And then you take a convex combination. This is indicated by this integral. Okay, if this looks a bit complicated, I have a pictorial version of this. So what the definetti theorem tells you is that if you take this big permutation invariant channel, now look at only n parts, then the n parts will look as n product channels. So you see, despite the fact that I've only traced out here the outputs, and there are in principle even these inputs, what this tells you in particular is that the other inputs here are not relevant for the output. So a permutation invariant channel really behaves as if it was a product channel, but this is the sum here, will be important. It's not one product channel, it's a convex combination of many possible product channels, each with a weight which is just given by a probability. So you can think of W here, which is over which I sum, as a random variable which tells you which channel it is. And once you fix W, it's just a product channel, but if you don't know W, then it's a convex combination of product channels. So it's basically an unknown product channel. Okay. Now, of course, if you have an unknown product channels, and this will be important, this is just an observation, you can calculate the entropy of just one outcome, of the outcome R1. So these are, let's say this is R1 here. But now you can do two different things. You can either just calculate the entropy of R1, or you can calculate the entropy of R1 conditioned on knowing which of the channels it is among the convex combination. And obviously you will get different values here. And this observation will be important for what follows. Maybe that's not yet clear, but I hope it's clear that these are different things. So either you look at the output just without knowing W, or you look at the output conditioned on W. Now, this is kind of maybe the most technical slide. This is a lemma that will be important to make the connection to black hole physics. So the lemma tells you the following. If you are interested in knowing the output of such a channel conditioned on this W, then you can calculate it actually by a formula which doesn't involve W. What you do is you just take the entropy of n different radiation, or of n different outputs together and divide by n, and you do that in the lemmas where n is very large. Here is the proof. Okay, maybe I go very quickly through the proof for the experts, and for those who don't want to follow the proof, that's fine. I think you just need to remember the statement. So here you just start with what you want to show, and then you use the fact that the Definetti theorem tells you that conditioned on W, it's a product state or a product channel. And product channels, of course, if you have a product state at the end, then you can, like the entropies are additive. Now, and therefore you can just write it as one entropy here. And then you use the fact that here the conditioning on W can be written as just the thing without the conditioning W minus some mutual information between W and R. And then the important observation is that W is independent of little n. So in the limit of large n, this last term goes away, and you're just left with this, which is the claim here. So basically the W doesn't need to be known in order to calculate the output of the channel conditioned on W. That's the very important observation for the following. So let's now apply this to black holes. And now I'll try to make a connection. So as you've seen before, what people are doing in these novel calculations, which gave the progress that led to the confirmation of the page curve, was that they're looking at n copies of a black hole. And of course, they could look at even more copies. And I said before that permutation invariance is an operational assumption. So what they can assume, and actually implicitly do assume, is that these n black holes are just unordered. So they have no specific order, and therefore they are permutation invariant, their behavior. And if this is not the case, you could actually enforce it by just actually shuffling them around. Now what the quantum Definetti theorem tells you is that the behavior of these n black holes, if they were quantum systems, if they were proper quantum systems, would be like a convex combination of individual channels. So each thing acts separately, but with an unknown channel, TW, that's somehow how one black hole behaves, and it's a convex combination of those. So that's I just plainly apply this theorem to black holes. Now the lemma I've shown you before is that actually when you calculate this thing here, you get really that entropy of R given W. So why is this now interesting? You can actually now give meaning to the two different curves and somehow say both Hawking and the new calculations, which I call, by the way, wormhole calculations for obvious reasons, are kind of correct. Because in this view, we could say that, and I will the argument is the following. So Hawking just looked at one black hole. He never looked at copies. And if you don't look at copies, you're just in the situation where this theorem you don't need the Definetti theorem, you just have one copy, and you get something out. But the actual R1 is somehow a mixture over all possible W's. Whereas the new calculations, which, as I remarked before, are secretly actually looking at n copies, are actually calculating this. That's what the lemma tells us. So the lemma tells us that if you look at n copies of a black hole and look at the joint entropy of them, that means that you actually, or that's equivalent to looking at one copy and conditioning on the W. And the W would be like, the dynamics going from M1 to R1. So in some sense, Hawking's calculation corresponds to calculating the entropy of the radiation without knowing the dynamics of one single black hole, whereas the wormhole calculation corresponds to calculating the entropy of the radiation while knowing the dynamics from here to here. So that's the first insight we get. The two are maximally divergent, as I said. I mean, SR1 is very big, as I've shown you on the first slide, and R1 given W at the end is 0. So there's a huge difference between these two calculations, and this suggests that this W carries a lot of information about R1. And this fact that W gives you a lot of information is somehow very well reflected by a toy model that has been proposed by Hayden and Preskill. They didn't talk about the W, but what I told you can be very nicely fitted into this toy model. The toy model is the following. So instead of looking at the black hole, I mean, they're quantum, I mean, at least, I mean, they're, of course, are both, but they in particular know quantum information very well. So what they said is basically, let's just model the black hole as a typical unitary. So unitary that you have chosen from a set, hard distributed set over all unitaries. And then you trace out some part that remains inside and look at and consider the radiation as just some other part of the outcome. So a black hole in computer science terms is just a random circuit, if you like, where you throw a part away and keep a certain part. And of course, if the black hole has evaporated completely, you don't throw away anything. So then it's just a unitary from M to R. And of course, that conserves the entropy. So that was a toy model that has been proposed quite early on I mean, already quite some time ago. Now I make a small modification to this toy model. So Hayden and Preskill said the unitary is known. It's just a typical one, but we know which one it is. Now I look at a different model. Let's suppose U is really random. So we don't know the unitary because, I mean, we don't know how a black hole behaves really internally, and I will come back to that. And it's really unknown. So it's random and unknown. Now, what does this mean in terms of a completely positive map? A random unknown unitary of n black holes, and I assume still all black holes behave the same. I just don't know it, which one it is, would obey this description. So I have a probability distributions about on all, and the summation over all possible values W, which describe the internal evolution, and then I have all the n black holes behave according or evolve according to the same unitary. So you see here, this picture is very much in alignment with this Definetti structure that we had before. So in a sense, this Definetti theorem supports that picture that actually a black hole is described by a unitary, but this unitary is kind of random and unknown. And this explains also the two results. So a Hawking's result would correspond here in this picture to summing over all possible unitaries within the entropy. So you don't know which unitary it is, and therefore you get a very high entropy, whereas the new wormhole calculations correspond to calculating the entropy conditioned on knowing W, but you take an average over all possible W's that you have. So that's somehow what this tells you. Okay, this is maybe a strange title, but it has often been said, a black hole is in a sense nothing else than a fire. If we know the initial state of the wood and everything we put into a fire, and then we collect all the radiation and smoke and so on from the fire, then we would see that if the initial state was pure, then the final smoke and so on is still in a pure state. That's of course true according to our current understanding of physics. So, I mean, I assume here that quantum mechanics is really unitary on all scales, and that's what these people always do. So it's even unitary on astronomical scales. And in this case, we would say a fire is just a very complicated unitary. But for a fire, we somehow, okay, this is my not very artistic picture of a fire. So for a fire, we kind of usually know, and we would say we know in principle the unitary. But here comes now the important point, which justifies this thing that I've said before, that the U is unknown. So suppose that I would put wood and everything into a box and then burn it and collect the smoke. And suppose the wood and everything would be described perfectly with all its microscopic degrees of freedom according to quantum theory, but not the box within which I burn the fire. Now, clearly, this box itself has an impact on how the smoke develops and how the fire burns. So I shouldn't do that in order to get a fully, let's say, unitary picture. I cannot just describe a part of a system just as a classical box. But let's suppose I do that. Let's suppose I describe it as a classical box. Then the classical box is a bit like a thermodynamic system in the sense that I've only given maybe the volume of the box or the diameter. So I only give macroscopic parameters, but I'm not describing the internal evolution of the box. And of course, for a given box that I describe to you, like if I give you the volume and so on, there are many possible unitaries that would describe the actual behavior of the box. Of course, one of them is the correct one for a real box, but all the others are also consistent with the macroscopic picture. So if I now did a calculation using this macroscopic box, it's clear that I would implicitly, or I would not say anything about this unitary, because it's just not described. So the end product of the calculation would in some sense be for a random unitary, probably, because it just doesn't incorporate the concrete unitary. Now, my claim here is that for black hole physics, it's actually very much the same, where the box is space-time, or the metric of space-time, if you like. And this is supported by the fact that, as you know, general relativity, the Einstein equations, can actually be derived just from thermodynamic principles. There's a nice work by Ted Jacobson from more than 20 years ago, where he showed that just by assuming a certain entropy functional and how entropy changes in space-time, you get the full general relativity description, or at least the Einstein equations back. So in that sense, you should think, or if you think for the moment, I'm not saying you should do that, but think for the moment as the geometry of space-time is something macroscopic. It's something like the box within which I put the fire. And there are many possible unitaries, in a way, or many possible microscopic degrees of freedom according to which the underlying microscopic things would evolve. But we don't know them, because general relativity doesn't describe them, and we don't have a theory of quantum gravity. So you can really think of a black hole like a fire in a box, where the box is still described classically. And then the same picture would apply. So we would say there is a random unitary, because we haven't described the details of the box. And then we can still kind of say, okay, one entropy is the one where we don't really know the details of the box, and another entropy would be a hypothetical one where we would know the details of the box, which are hidden to us, and calculate that. Now, the amazing thing about these new calculations that have been done by Pennington and others, these wormhole calculations, is that they somehow give you that thing that is conditioned on knowing the microscopic dynamics without actually putting that into the calculation. And the reason why that works is really now in the view of information theory, the Definetti theorem, which tells you that actually this thing is just equal to that. So you actually really don't need to know the microscopic dynamics. You can calculate this entropy just from having n copies of the black hole. So in other words, the same would in principle apply to the fire, but there I'm not aware of a calculation that does that. But so for black hole physics, it's the case that you actually calculate this, and what it really does for you, or what the Definetti theorem tells you what it does, is it actually calculates the output of the radiation as if you did know the internal dynamics of the black hole, despite the fact that you don't know it. So that's what the Definetti theorem really tells you, that these two are equivalent. Okay, now I'm almost done. This is just, before I conclude, you could ask, where is now this W? I mean, there are some microscopic degrees of freedom, and in this space-time picture, and we know there's somewhere the initial matter, there's somewhere the radiation, but where is the W? So, of course, the W is something beyond space-time. It's the underlying degrees of freedom. So we shouldn't try to put it here somewhere. I just put it here as like the thing that determines the evolution, the microscopic evolution over time. So the W is something hidden behind space-time that tells us how things evolve. And now the question is, how does the path integral actually incorporate this W? So as I said, the path integral approach really calculates that, and I told you that it does that by looking at many copies, but how is this really working? How can a calculation that doesn't know about W at the end give this result. Okay, sorry, this should be an S according to my convention. Now, the wormhole come back, because this is really, you can now understand that this is exactly what the wormholes do. The wormhole, so as I told you at the beginning, what these people found, which did the path integral calculation, was that the geometry they need to consider is one that connects all these little black holes in the inside. And actually connecting them in the inside is kind of, in a way, equivalent, I didn't show that here, to actually extracting that information from the black hole. So in a way, the wormholes are the geometric means to extract the information out of the black hole about B. But knowing B, okay, I forgot to say that here, although I put it in red. Knowing B and R, so if I know B and R, this is, and I know M, this is, then I also know the evolution, then I know how M translates to that. So if what the path integral formalism actually does with these wormholes is it extracts the information about B, and R is anyway at the outside. So together with R, it extracts the relevant information about W. So the meaning of the wormholes that have this are kind of appearing in a magic way, or the purpose of them is to get this information about the hidden dynamics, which is in the black hole. So they somehow extract that. Okay, now, as I said, this sounds maybe still surprising. So one can now do some plausibility checks just to see whether this model that I proposed, that we have basically like in Haydn-Preskill a random unitary, but the random unitary is unknown, whether this is plausible. And in order to do that, you can do two calculations in two different frameworks. You can once do the calculation with the path integrals, these modern calculations, and you can just do a kind of quantum information calculation where you use random unitaries. And you can do that for more complicated situations. So you can, for example, do the following. You create a big black hole and let it evaporate for a certain time until it gets smaller. Or you create just immediately a small black hole. And then you do these two things in a superposition. So if you do these things in a superposition in such a way that when you create a small black hole, it's just the same size as when you started with the big black hole and it already evaporated radiation away, then in this superposition, the state you have is a black hole of a fixed size, but the radiation is in a superposition between having already radiated away a lot and having radiated away almost nothing. And this is just to show you that actually the two calculations agree. So one can now do these calculations with the path integral approach, and Jin-Sao Wang did that. These are kind of complicated, and you can do them also in this unitary picture. Then there I did it, and they're much easier. But the two plots actually agree. So this really shows that this picture that the De Finetti theorem tells us seems to be actually quite accurate one, even in regimes that we haven't tested before. Okay, so this brings me to the conclusions. So we started with this black hole information puzzle, and as I told you, recent calculations tell you that this should really be the correct description. However, what the De Finetti theorem tells us is that we can actually give meaning to both descriptions. You can say that what Hawking calculated is really the entropy of the radiation, not knowing the internal dynamics of the black hole. And what the new calculations do, which look at n replicas, they actually calculate the entropy conditioned on the unknown dynamics. And the amazing thing, which the De Finetti theorem explains why it's possible, is that they could do that without knowing this. So they could really calculate this quantity conditioned on an unknown dynamics without knowing the dynamics. And they lead to this curve here. So in that sense, everything seems to be consistent with the fact that the actual evolution is unitary. And of course, if you don't know which unitary it is, then we still have a lot of entropy. Okay, this brings me to the end. So this is, by the way, a picture of Jin-Sao, whom I mentioned several times. He's really amazing at doing all these calculations. And I also would like to thank other group members, in particular, Laura Guri and Giulia Massola, who started recently to work on this topic. And of course, all of you for listening.
Thank you, Renato, very much. First Nicola, then Czaslaw.
Thank you very much for this fascinating talk. I have two questions which will illustrate my ignorance. So you had this analogy with the fire, and then you said in a box, and we don't know exactly the box, so we just describe the box classically. So how do you then go to many fires in parallel, let's say with the same box for each of them, but in such a way that at the end, the box doesn't matter?
Yes, okay. No, this is a very good question. I don't think it has any... Okay, you're never ignorant. I will wait for that moment. So actually, one thing I should have said, which is maybe a surprising part of the surprise, is that when you look at the path integral calculations which do this, then you take replicas of the black hole. Now, of course, a replica could in principle do two things. It could take a replica where the part that we have described classically is just replicated, but there is a new instantiation of that, and maybe the classical degrees of, the degrees of freedom that were left open by the classical description are again different. So if you would somehow reproduce the fire and manufacture a new box, then for sure it will have like a different microscopic dynamics. So what actually happens in the black hole calculation is not that. It's as if you would perfectly replicate the box with the fire. So it's somehow a technique that, that's maybe the remarkable thing about the technique, reproduces the box, which is space-time here, which is kind of classical, in a way that copies also the internal degrees of freedom without knowing them in a way. So it's as if you have a condition that ensures it's the same macroscopic degrees of freedom, but you don't fix them. So it's as if you had a machine that knows more than you. So the machine would really copy the firebox perfectly, but it doesn't tell you what it exactly is, what its microscopic states are. But you have to guarantee that it's a perfect microscopic copy of it.
Okay, not sure I got it all, but we'll talk more. Here on this picture, that's my second question. So you have these wormholes, and I remember hearing and listening to talks where people then were saying, oh, and these wormholes, they are connected to entanglement. So the first black hole is entangled with the second one, and the explanation is wormhole. But now with this definity theorem, you, on the contrary, say that these black holes, they factorize, at least a subset of these black holes, they are equivalently described by a factorized set of black holes with tensor products.
Yeah, that's right. So, of course, wormholes appear in different discussions. The wormholes that appear here are really of the type that they connect n copies. And what the definity theorem tells us is that then the correlation is really a classical correlation. So the W is actually classical. So in this case, of course, you can always purify it and then say the overall thing is entanglement. But the nature of this correlation is a very classical one. That's true. But this is not in contradiction to other scenarios where people look at wormholes between just two black holes. But it also explains, I said at the beginning that when you, for example, want to extract, you want to extract information from a black hole, you simulate it. Now, what this means is that if you also describe, I said that if you describe the simulator also on in the path integral approach, then you get this kind of funny result that the simulated black hole is also entangled with that. Or, sorry, in this case, it's also connected. In this case, you have just two. So here you may think of entanglement. And you could indeed say that the reason this works is that the quantum computer that extracts it has to be in these hidden degrees of freedom correlated to the black hole, which makes sense because how should the quantum computer be able to retrieve information from R without knowing the internal dynamics of the black hole? So again, the wormhole, what it does is somehow to make sure the computer also knows the internal dynamics of the black hole. So that's a way to think of this. That's maybe a bit too sketchy, but you can really think this is necessary because without that, you have again, like for the fire, this would connect the computer to the knowledge of what is really the box, what is it made out of. And if you didn't do that, then the computer would say, sorry, I cannot reconstruct it because you used the box, which is just classically described and has too many degrees of freedom, which I don't know. So it has to somehow connect to that fire. And the path integral approach does that automatically somehow.
Hi. So I would also have a question about path integral approach, and I didn't get this fully. In the very first slide, when you connect, I think a single copy entropy with the n copy, like in the equation, yeah, that's exactly. So at some point you said, so my question is the following. So it seems like that when you go to the n copies, you can extract more information than where it's, but from the second term to the third term seems to be just a kind of algebraic equality, and so it's not obvious where this new information is coming from, taking the n copies instead of only one copy.
Okay, yes. So, okay, no, this is a very important point. So maybe first I should say these pictures are slightly simplified in the sense that to do the full path integral approach, this is like only the ket if you think of the path integral, and usually you have also a bra, so you have a mirrored thing, and then the wormhole is kind of also involving them. But I think this was not your question. So your question is, this thing is just an algebraic thing. So, but I would say this is actually the operational thing. So this is a thing that has not an operational meaning because the state of one single system is in a way not operationally defined. If I give you one black hole, you have no operational means to find out the state, and therefore you couldn't calculate this thing. But if I give you n copies of the black hole, you can apply this operator, or you could do, if you want, you could also do tomography and find out rho, but in any case, you need several copies of it. So I would say operationally, you're already forced to have n copies to actually give a meaning to that quantity. So I would say this equality is actually misleading. What it really means, so if we write such things, we mean that if we had a source which would produce so many copies of a system that we could determine rho, then we could calculate the entropy. So hiddenly, this thing is already something that operationally only has a meaning if you have n copies, and this just makes this explicit, I would say. You don't look very happy with that.
The first term contained this information already there.
I would say somehow we should always have started from this, and so we want to talk of course, I mean, about physical quantities, and physical quantities have to be measurable in some way. So I would say entropy should in the first place somehow be defined in that way, and this is somehow a shortcut which we misleadingly interpret as something of one system, which it's not. Maybe that's the better way to see it.
Okay, I apologize. We'll have time only for 2 more questions. We go online now, and there is one question was asked a long time ago before there in the last row, and I kindly asked the rest to ask Renato during the coffee break. So we go online now. Hello.
Hi.
Hi.
Yes,
Hi.
I have a similar question about these different copies of black holes. It seems to me that the wormhole connects different copies of these black holes, but I'm not sure how to understand so many copies of black holes, especially when it goes to infinity.
Mm-hmm. Oh, yes, there was the infinity. That's a good question. So, so we need many copies. However, all the theorems that I've shown, the Definetti theorem in particular, they have finite versions. That was actually one of the results that were, surprisingly, most of the things that now appear in black hole information have at some point been developed in quantum cryptography. Definetti theorems, mean entropies, max entropies, recovery maps. And so one of the things that has been done in cryptography is to develop finite size versions. So if you replace all infinities by finite numbers and keep track of the epsilons, like how well do you approximate things, then everything still works. So it would just look a bit more complicated. So I could give you an explicit number, like if you want to calculate the entropy up to a certain precision epsilon, then I could in principle tell you, you need n equal to probably something like 10 to the high number copies of the black hole. It will be a rather unrealistic number, but I could give you an explicit number, so it will not be an infinity. So the short answer is the infinities can always be taken away in the same way as, to refer to Nicola, she's real numbers one can get rid of and replace them by something else, which is very important. So these are not physical things, but we can approximate everything and get the same results to any arbitrary approximation without infinities.
Very good, thank you. And last question.
Maybe a question on with respect to which observer has now unitarity been recovered, so or restored. Is this an observer that lives in one asymptotic region, or sees a superposition of? Because any realistic observer can only see one, lives in one asymptotic region, that doesn't see n copies. Mm-hmm. So what is the observer with respect to which unitarity has been restored in this image?
So yeah, the answer is of course an answer within the current theory, because the knowledge we have is also depending on the theories we have. And so what the answer that is now given within the most advanced calculations, which involve this path integral approach, is that if you had only one observer with only one black hole, then the Hawking calculation would correspond to the entropy he sees, because he has no chance to see the internal dynamics within that theory. So I'm explicitly making constraint. We are now talking about the theories we have currently and all these calculations that are made within current theories. But of course you could imagine an observer in principle who creates many black holes and uses or simulates some, that was this idea with the quantum computer, and uses this simulation to actually find out something about the W, and then he can reproduce that. So I would say an observer, typically you have these observers who jump into black holes, he will only see one. And for him, it's always the Hawking type thing that is relevant. For someone who stays outside, who could in principle create copies of a black hole, and if he does so and uses them, for that observer, the new wormhole calculations would be giving them the relevant thing. But he has to exploit that information. He has to really retrieve it and reconstruct the W from what he sees and so on.
Very good. Let's take Renato once more.